So as you know, the subject for today's roundtable is I/O for the future, and we have three experts in the field who are going to be talking about their respective fields of expertise. And the first speaker today is going to be, well, actually, you see a nice little graphic, actually, courtesy of Marcus here. So you actually already know what these speakers look like, just in case they're a little bit shy today. But Jakob is going to kick us off. So he's going to be talking about RNTuple and the status of and plans of Root's I/O evolution. Jakob is in the SFT group at CERN, bringing us all kinds of goodies, and Root and RNTuple, of course, are very much of interest to the whole field. So Jakob.
Yeah. All right. Thank you for the invitation. And I'm happy to talk about RNTuple, which is Root's R&D program for the event data format and access API evolution. So it is, if you will, the successor or the designated successor of T3. And so if we look at high energy and nuclear physics event data I/O, of course, in the Root team, we think there's a good reason to invest in tailor-made I/O systems, which is T3 and hopefully soon also RNTuple. So the first reason for this is to have an I/O subsystem that is capable of expressing our typical event data model. And our typical event data model are nested interdependent collections of floats of data points. And I've shown one like toy EDM on the right side. So inside an event, we typically have vectors. We have vectors that are somehow connected to each other, like particle and tracks. And of course, we don't know upfront how many particles and tracks we find in each and every of those vectors, of those events. And we also want to have, of course, something that is very much performance tuned for the analysis workflow. And that means a columnar binary layout. That means that what we see, that typical analysis workflow doesn't need each and everything from an event, but a subset of features, let's say PT. And we want to store it in such a way that all the PTs are next to each other. And we don't have to jump from PT to PT through the events. So that's the columnar layout. And a columnar layout for variable length collections is something that only very few other products support on the market. There's Apache Arrow and Apache Parquet, and that's pretty much it next to Root. Now, one very unique feature of the Root I/O is the close connection to Cling, and Cling and with PyRoot also Python. So which means that we can generate the schema of our data automatically from the C++ code, and that is let me see. Is this my sorry? Is this my email client that makes a noise? Maybe.
I didn't hear anything, so.
Oh, okay. So probably mine. Right. So we can generate the schema automatically from the C++ code, and that's very different to most. I think to every other product where you have to have an explicit schema generation step. Then we have some typical tools, federated data management tools, XROD and so on, and it would be nice if we have a good integration. So this is also a reason to have hands very tightly on the data format. And of course, we know that the experiments run for a very long time, and we want to have a good maintenance and support of the data format during lifetime of the experiment and beyond. So the motivation to take a fresh look at T3, which served us well for many years, is twofold. From the one side, we know that HLLHC poses a much bigger challenge than we have today. So we expect to have more or less in every metric factor of 10 times the current demand. Certainly like a number of events and what this exactly means, like how the relationship between recorded events and events you need for analysis, there might be, this might not be exactly a factor of 10, but let's say for the sake of simplicity, we expect a factor of 10 increase in number of events that we want to analyze. And at the same time, which is actually good, we see a change in storage hardware. So we have, by now we have ultra-fast networks, we have ultra-fast SSDs. So we see 10 gigabyte per second per device is very much reachable. And traditional storage systems have been designed for HDDs, which have more like a few hundred megabytes per second. These storage systems are inherently parallel. So that means we need to access them with asynchronous parallel I/O. That's key to get performance. And we also see on the CPU side, the heterogeneous computing hardware, for instance, with CPUs and GPUs working at the same time. And what we ideally want is possibility to have GPUs load data directly, ideally directly from SSD, and this is possible today, for instance, to feed an ML pipeline. And then if you look at distributed storage systems, there's a move away from POSIX, so from file-based storage system, to object stores, which have a simpler interface. There's no directory tree. They are simply objects, but they scale better. So this is the reason why this is an interesting technology for ultra-scalable, for instance, HPCs. So like as a concrete example, if you have 10 gigabyte per second from the I/O device, and you process the typical route 32 kilobyte baskets, you have about 3 microseconds per basket. So CPU optimizations that we typically only did for very compute intensive code, they also now find their way deep into the I/O stacks. Right. Yeah. So
Jakob, are you
yes.
happy? Just to let you know, so this is not presentation mode, so we can see the comments, and I'm not sure if there's going to be
yes
anything sensitive from Axel.
Actually, yes.
I think on top right you have to click the present button next.
Thank you.
So while I have interrupted you, can I just point out the live notes there actually? So if anybody has comments or questions that they would like to ask, instead of asking them directly during the talk and interrupting as I'm doing, it would be great if you could just add your question to the live notes, add your name and affiliation, and then we'll come to those questions at the end. So apologies for the interruption, Jakob.
No problem. Thank you. It's actually very helpful. So based on all the experience we had with T-Tree, we would like to redesign the I/O subsystem slightly with RNTuple, keeping the best of T-Tree, but adjusting to modern storage hardware. And first and foremost, I mean, to have a good reason to do this, we need to have a proper goal, a proper gain from this, and this is smaller files and faster access. And what we think, what is realistic to expect, something like 25% smaller files after compression, and several factors better single core performance when we access the data. And like in absolute values, what we like to sustain and show what's possible is 10 gigabyte per second per box, or at the same time, 1 gigabyte per second per core, end-to-end throughput. So from compressed data to histograms. Then we would like to natively support object stores, especially important for HPC systems, future HPC systems. There's a R&D line that looks into lossy compression. So that is not the 25% smaller files, but lossy compression, of course, can get us much more. It's not directly related to the file format, but this is more a question of how to figure out which precision is necessary for any given analysis. But what the file format needs to be able to support is a flexible mechanism to store floats in various like, let's say, various precision level. And so one very like practical goal is we would like to avoid silent I/O errors. So as part of the interface modernization, one very important point is to use systematic crashes whenever something goes wrong, right? So what you do not want from the I/O subsystem is that it continues and you might get wrong data. What you want from the I/O system is that it crashes and you know something went wrong. So that is, of course, a larger undertaking. So this gives you a rough development plan. That is not set in stone, but just to give you a little bit of an idea of what we think is realistic for the RNTuple prototype to make it from proof of concept to production. We started with this around 2018-19, have a first prototype with which we can make a solid performance validation. And now we are entering a first exploitation phase. So we are now this year and the next year interested in how does RNTuple interact with experiment frameworks, how can we do things like schema evolution. So this will keep us busy the next 1 to 2 years. And then we are entering slowly a pre-production and production phase. So all of this is to say, we see this as a run 4 technology. It is available, nevertheless, now in root experimental. So please feel free to look into it, to experiment with this, give us feedback if you want. And perhaps one important note, so all of this does not mean that we are going to abandon T3, but we are well aware of the fact that we have more than an exabyte of data in the T3 format. So this will remain available and supported. So a little bit on the class design. The RNTuple has several layers for the data access, and so there's at the very low level there's a storage layer, so that we can read and write byte ranges. On top of which there's a primitives layer. So the primitive layer represents storage-backed columns, very large arrays of fundamental types, floats, ints, that are grouped into pages and clusters. And on top of that, we have a logical layer for the C++ objects. So the logical layer defines how more complex C++ objects get mapped into a primitives layer. For instance, a more complex C++ object might be std vector or float. And an std vector or float would be mapped into 2 columns in the primitives layer, 1 column for the floats and 1 column that tells us about the size of the vectors. And what the user interacts with is the event iteration API. There's a custom API for our RNTuple, but what's interesting here is that we integrate this with our data frame. So our data frame being Root's facility for declarative analysis. And the idea is that should you have your analysis expressed as an RData frame piece of code, you can seamlessly exchange T3 and RNTuple data source. So you would not need to change your code to analyze with one or the other format. So we put some effort into making this layering fast. So it has a minimal, hopefully minimal overhead. Most of the time you would go with C++ templates directly from event iteration to the bytes of the storage layer without making any implicit copies. And another important point of keeping a good layering is that we can, of course, start to exchange things in the layer, especially in the storage layer. So we could use a file to store the byte ranges of an RNTuple, for instance, a root file, but we can also use something else, for instance, an object store. And I will show a little bit later what we have done in this respect. If you are familiar with T3, here you see a rough translation of class names, just to help you navigate a bit. So the file format breakdown shows how data is being laid out on storage. An RNTuple has a header with a schema definition, so which fields do I have, and a footer. The footer tells us where I can find certain data, pieces of data. For instance, if I look for the 1000th event, the FID, then I would look in the footer to tell me in which page this is. And then we find as the actual data layout the different features of our data set laid out in columnar storage. So for instance, like this is here color marked for the FID, we have them all, or many of them from the first event, second event, third event, and so on, one after another. And we group this into pages and clusters, so into blocks of sizes that work well by some definition of well. The idea is that a cluster contains all the data of a certain event range, and they are more or less independent from each other, and more or less typically they have like 100 megabyte in size. And the idea is I can take the cluster and use it to distribute it on several machines. So I can give every machine a particular cluster. And inside the cluster we have the pages. These are the units of memory mapping or compression and decompression, typically 100 kilobytes in size, right? I mean, the root T basket is similar, like with a standard size of 32 kilobytes. And one nice thing that we managed to do with our RNTuple is inherent parallel decompression. Soon there will also be the compression part, but for now we have implemented the decompression part. So you can do root enable implicit MT, and behind the scenes, root would use all your cores to decompress in parallel. So that's of course fantastic if you have a very strong compression algorithm like LZMA, and you can use all your cores to do the hard decompression work, and you get almost the speed from an uncompressed data set, provided you have enough cores. Right, so if we compare RNTuple to T3, I mean, the general structure is very similar, but there are some important changes. We have a more efficient storage of nested collections, so they compress better because we separate better the offsets from the data. We have a more efficient storage of booleans, which are stored as bit fields in RNTuple. So that's very interesting for trigger bits. And we are just now started to experiment with split floats. So the idea is here that we pre-process a little bit an array of floats to make it easier for the compression algorithm to do good work. And it appears that we get some percent out of this, sometimes significant for the weak compression algorithms, more like 10% or more. But even for LZMA, you can still get a few percent. Little endian values, so it maps better contemporary CPU architectures, and in general, a good and tight control of the memory that you use for I/O. So compared to T3, the type system is less powerful. At the moment, we have a supported type system for Boolean, integers, and floats, string, vector array, variant, and user-defined classes with the help of Cling. We plan a few more classes. For instance, one of the interesting one would be STD Chrono to support as a supported type. But so within this whitelisted type system, everything is fully composable. So you can have vector, of array, of variant, of Boolean string. So within it's fully composable, but you are limited to this whitelisted set of types with which you can do I/O. And that has been a conscious choice to have like optimal support for those types that are actually needed. We use a few standard benchmarks when we do performance evaluation. And at the moment, we have put together 4 standard benchmarks that we use. and we try to have a bit of a variation in different EDMs, different like sparse reading, dense reading, and so on. So there's LHCb Run 1 open data, there's the Atlas 2020 open data, then from the H1, the very old root standard benchmark, and also CMS Nano AOD. We'd be happy actually to add a few more. We have made the experience that is not easy to find a good benchmark. So it's not only about like a dump of data, but you need to have some data in a simple EDM that comes with a toy analysis that is that tells you something, yet is simple enough to write it like in an afternoon in few different variations. So at the moment, it's a reconstruction of masses in most cases. But if there's something from nuclear physics that would fit into this category, we would be quite happy to get a pointer and maybe write to me if you have something in mind so that we can edit. So some selected benchmarks. This is from 2019 from CHEP. On the left side, you see comparison between T3 and RNTuple for the CMS Nano AOD, and it's the file size that we show here, uncompressed and then with several compression algorithms. And we see that we get substantially smaller files, and even with a very strong LZMA compression. So the improvements that we put in the file format, they actually survive the compression. And also an example for SSD reading, where we see that also with RNTuple we get significant faster read times, more throughput. And we see something very interesting here, because so often when we do benchmarks, we compare data that is already in memory. But in real life, we read data from an actual device. So there's a trade-off between how much CPU power do I put in the decompression and how much data do I have to read from the device. And we see there's a sweet spot here for the ZSTD compression algorithm, which is the default for RNTuple, where we do have to put a little bit of CPU effort in the decompression, but because the compression algorithm is strong, we also read fewer bytes from the SSD. So, and that is the fastest we find is at this spot of the phase space. So this is a continuous effort. By now we have done a few improvements, so this plot would look slightly different with the current master branch. We also would like this year to compare this with HDF5. We have done this in the past, last time in 2017, but there we compared T3 to HDF5 and found that T3 does actually quite well in comparison. But now after 4 years, it's time for an update. Then an interesting result that we found is that it really pays off to read in parallel from SSDs. So what this tries is, or what this shows, is the difference between reading like with a single stream compared to reading in parallel with multiple streams. And so for this benchmark, this has been really done with multiple threads. But by now we have implemented this in RNTuple using async IO with liburing. So this is the new Linux kernel facility for async IO. And then the nice thing about this is that the kernel does all the multi-threading handling. So we do not have in the program to deal explicitly with threads. And we see that we get very good throughput from this. So with recent consumer hardware, we get 4 GB per second raw read performance with this approach. And the last performance plot I want to show, this plot actually shows that a key for good performance, if you read from actual block devices, is to use a real I/O scheduler. So in this plot, I would like to especially point out the purple bars to the right side. And we see here, so what we compare here with those purple bars is mmap versus explicit read calls. Like naively, you might think mmap gives you the best performance because you don't need to make a copy from kernel to land to user land. However, mmap doesn't know anything about the data layout. So mmap will start reading data from the disk as it sees fit, as the read requests come in. In RNTuple, however, and also in T3, we have an explicit I/O scheduler. So we know upfront pretty exactly what we are going to read, which columns and which pages we are going to read. And we can collect this information and then put, for instance, coalesce the reads and make one big read for a continuous chunk of data that we are going to read from SSD. And even with SSDs, which have pretty good random access performance, they are still block devices. So we still win by using explicit I/O scheduling. So now switching a bit topic to distributed storage, RNTuple and object stores. That is also one of the goals, that we have native access for object storage. And we do this because we expect that future HPC systems will more and more be using these object stores instead of shared POSIX cluster file systems, simply because they scale better. And one example where an HPC is going into this direction is Argon's Aurora, which will provide 220 petabytes of Deos object storage as the main storage for the machine. And we want to support that with the implicit goal to, if possible, to avoid that you have to do transient copies, right? So we would ideally want to avoid making a copy into some other storage system or file format just to be able to use an object store. It would be much nicer if you could use it just as is with root data. And if you look into, so first of all, the API is actually doesn't change at all. So it's really transparent use of object stores that you can see in the first line. You open the ntuple, you specify the ntuple name, and you give, instead of a file path, you give the ID of, in this case, a container, a Deos container, which, okay, in case of Deos, happens to be a UUID. So you map an ntuple to a container, and it's actually very nice, this Deos system, because it allows us to map the RNTuple concepts to concepts of the Deos system. A cluster of, let's say, 100 megabyte would become an object. So if we do, for instance, reconstruction, we could read the entire object in one go. But if you do analysis, we can go into that object, and every object in Deos is itself a key value store. And it has two types of keys, a distribution key and an attribute key. So this gives us the possibility to go very fine-grained into the object and read exactly what we need. So the page group in this case are all the pages with the same color in a single cluster. So we could read like all the green pages in one go, which are all the pages of one column, let's say PT. So that is the mapping that we have currently implemented. We have run first performance tests. This is kindly, so CERN OpenLab kindly provides us with a Deos cluster, 3 servers and a client. And we compare this to local file on SSD and to dFuse, which is a fuse compatibility layer for Deos. So if your application is not ready to use an object store, well, you can use Deos as a distributed file system, but it comes, of course, with a performance cost. And like the first goal is reached, we are faster than the dFuse compatibility layer. We read at the moment with about 1 gigabyte per second. This is ongoing work. We think that we should actually be a lot faster than that. And yeah, we hope to achieve this soon. Then another ongoing project is the integration with experiment frameworks. In this case, is CMSSW. This is a project which is kindly funded by Iris HEP, where the idea is to use the CMSSW output module to write nano AODs in the RNTuple format. So nano AODs is this very compact format for CMS data that is like very much compressed or very much slimmed down, yet powerful enough to work for the majority of analysis. So it's 1 kilobyte per event, approximately. And it should help us to get the first experience with framework integration to allow for tuning of multi-threaded writes. And of course, to do then some large-scale comparison, because once we can generate lots of nano AODs in RNTuple format, we can then compare T3 and RNTuple on a large number of such data sets. So roots, RNTuple is roots IO R&D, aiming at a leap in data throughput. It is an updated and actually backwards incompatible data format for the next generation event IO, where we expect significant gains, smaller files, faster access times, optimal use of modern storage devices at their full capacity with a modern and robust API. And we are now entering the first exploitation phase, and I put a link to the program of work 2021 if you are interested in more details. Thank you very much.
Thanks a lot, Jakob. So virtual round of applause. So what I'm going to do now, let me just check that Andreas, our final speaker, you don't have any time constraints?
Oh, no, I have no problem.
Okay, so I'd like to take a few minutes now just for questions. And I'm going to switch. Oh, I cannot share while the other participant is sharing. That is, let me try again. Sorry, Jakob.
No problem.
Okay. This is experimental, so I think that's the right screen. Okay, so we have a few questions in the live notes, and let me just go straight to them. So the first questioner is Doug. I know you know where the unmute button is, Doug, so do you want to go ahead?
First question is, you've done a bunch of good work on DAOs. Are there plans, and it looks like from your talk you use some DAOs features. Are there plans to evaluate other object stores like Lustre, Ceph?
Vague plans, nothing concrete for this year. I think that Intel DAOs, especially due to the fact that Argon is going to use it, is the most relevant one. I think the next very relevant
DAOs
one
is delayed. Argon's delayed, whereas Lustre Object Store exists.
All right, fair enough. That's
and Ceph does too, right? I mean, CTA uses Ceph
yes.
Object.
Yes, so probably S3 would be an interesting one because it's very general and it gives us access to the big data ecosystem. So this would be high up on the list. Now, taking into account that you say Lustre is earlier available than DAOs, we might take a look at this too.
Okay, Doug, do you want to move on to your second question?
Yeah, in one of your early slides, you talked about trapping the error and just, is it the idea to be able to propagate it all the way out so programmatically the upper layers of code can deal with it?
Yes. Exactly. So this in C++ exceptions would give you that exactly that functionality. And of course, then it's up to upper layers in the code stack whether they want to do something about the error or not. But it means that if nobody does anything about error handling, the program crashes. And that is exactly what we want.
Yeah, right. Thanks. No silent errors. That's good.
Yes.
Indeed, yes. Okay, so the next questioner is a young man called Paul. Let me go ahead. So I was interested when you were talking about the layout, and you said that the page size optimization kind of works in some definition. I'm paraphrasing, but could you comment a little bit more on that? And is it customizable?
It is customizable. We haven't spent a whole lot of time to optimize. We have taken more or less the values from T3, the defaults, because they are there. But it is something that we should do at some point to make a parameter scan, which page size works best under which circumstances.
Yeah, I can imagine that could lead to a lot of scanning the parameter space for these optimizations can take up a lot of time. So that might be worth thinking about also in terms of providing an API for working out how to do that so that you don't have lots of different parameters to worry about. Okay, so a similar kind of theme, but you said on the last slide actually that this is incompatible. So I was wondering about a migration path from T3 to RNTuple, maybe even for experiments. How do you see that happening?
So I think that the use will start with data products that are at the very end of the chain. So on final stage n-tuples that are easy to recreate. If we screw something up, worst thing, we recreate it. And then experiments would decide at some point, hopefully based on the merits of the new system, to move its use more and more up into higher or deeper layers, previous layers, stages of data products. So like reconstructed data, at some point, perhaps raw data. Yeah. So that's the adoption. Okay, so
you can see how it's applicable to the analysis use case in particular, where you're being very selective about your data. So a columnar layout is going to make a lot of sense. So, okay.
Can I comment on that? Sorry,
sure.
Marco Scatano. Yeah. So I'm thinking of the kind of nano AOD type of use case. And suppose LHCb were to move to this in run 4, which for LHCb is not a new big step. It will be just an increment of run 3. We would want to be able to analyze run 3 datasets with the same software as the run 4 datasets. And somehow we need that compatibility, or we need a path to convert the T3s to RNTuple during LS3.
Right, so conversion, of course, like disk to disk conversion, this is always something that's possible, but it comes at some cost. Yeah. On the side of the code,
API is very incompatible, you said, right?
The API, like the low-level RNTuple API, is incompatible with the T3 API on purpose. So we wanted to have something that is modern, robust, C++. However, as long as the code is expressed in terms of our data frame, it's actually very much compatible. So our data frame makes it seamless. Because for a data frame, you simply exchange the data source, that's it.
I guess that works for end user analysis, but still for the software framework developers, etc., then there's going to be some pain there. But okay. It is, should we move on to the next question, or are you happy, Marco? Or unhappy about the answer?
Yes, thanks. Happy.
Okay, thanks. So the last question is from Thomas. Go ahead, Thomas.
Yes, hi. So in principle, it's somewhat related, I guess. So basically, what are the requirements that EDMs that are built on top of RNTuple, do they have to inherit from T-object, or are there any significant changes with respect to T3-based ones? I mean,
right. Yes. So they don't have to inherit from T-object. This was something we wanted to do. It's in a way it's a bit more limited, and especially when it comes to pointers. So we don't have the general pointer support that that you find in T-tree. We might add references of some sort. It's not yet fully decided. This is also, we are also still trying to figure out what are the essential parts of an EDM that absolutely have to be supported. But on the other hand, there are also some things that are supported in RNTuple which are not or poorly supported in T-tree, especially when it comes to modern C++ constructs like STD variant, STD optional. These things are much easier to put into RNTuple. So what we hope is that we find like this usable set of types of a whitelisted type system that is powerful enough to capture the data, and perhaps not so general that it prevents us from performance optimizations.
Right. Yeah. That, I mean, that sounds very reasonable. Looking forward to where this is going in the end. Thanks.
Yeah, I mean, if you have any concrete input for me or for us, like, you know, this is a type that we absolutely have to have, which you might not have thought of, let me know and let us know.
Yeah, we'll definitely do.
Very good. And I'm sure there are a couple of people who are listening and hearing that invitation to think of RNTuple test beds as being an interesting project to engage in. So okay.
Yeah, I did. I mean, you just touched on it, but I wanted to ask, but I think it's worth mentioning again, you didn't talk, and you didn't mention at all in your talk about associations or pointers. And I don't, yes. I'm surprised you don't consider that to be an important part of an event data model. To me, that's almost the whole model.
Right. I mean, for instance, again, if I look at the nano AODs, in this case, it is simply solved on the application level with like index numbers that put together then the connections. As I said, we haven't made up completely our mind about this. Probably we need some sort of format level association, like that you can connect, let's say, particle and tracks in the same event.
I mean, I was even going to go further and ask for smart pointers, that I have my track holding hits, and can I, if I keep that track, can I keep just those hits?
Right. It is an interesting question.
I mean, this is part of this is motivated by kind of moving beyond just a simple, distinct event model where you have one event, and and you keep that whole event, but you want to keep parts of events, or you want to even mix different events. You want to build a new event out of other events.
So yes, so that is right. That is an interesting use case. It's probably, so the inter-event relationships is, I think, not something that we would support in the first iteration of RNTuple. But we would leave then certain part of the job to the user code on top of it.
I mean, when we use many of us use T-tree, maybe not the standard AODs, but we use T-tree. Our events aren't events. They're often something else. They're tracks or hits. I mean, they're right. When I make T-trees, I make a collection of something, but it's not necessarily a HEP event.
Oh yes, so I use event like interchangeably for entry or for like a struct. Let's say a struct with stuff in it.
Okay, so I think that's. I'm going to suggest we wrap up this discussion just here, David, if that's okay, just in the interest of time. But I think that Jakob, you have some interesting feedback as well yourself here,
Yes.
so that's already good. So good to start this conversation. Thanks again. So let's move on to the next talk. And the next speaker is Peter from ANL. He's going to be talking about the HEP-CCE IO and storage project plans and progress. So straight over to you, Peter.
Yeah, thank you very much. I hope you can see my slides or my browser with my slides.
We see the browser, yes.
Okay, that's as good as I can go. Yeah, first of all, thank you to the organizers for having me over and introducing you to the HEP-CCE project, or the High Energy Physics Center of Computational Excellence project, and especially the IO and storage part of that. And I will present for the group, I will present our plans and progress. So why is a HEP-CCE? We heard some of that already. In HEP, computing resources will face a challenge with our increased experimental resources, really the LHC upgrade and so on, giving us more data to process, which then needs to be processed on computing resources and stored on storage resources. So we will need about an order of 10 more data, and we have an order of magnitude more of complexity within our events at the high luminosity LHC. So that will require order of petaflops of sustained computing power per experiment. So if you look at the plots on the right-hand side, you might have seen them before. It shows our estimate for computing resources and storage resources needed for that high luminosity LHC timeframe. And you see that we are much higher than what we can expect to have provided by our current budgets. On the other hand, the US and other countries really have made a long-term investment in high-performance computing. And you see on the lower plot that those high-performance computers have made major steps forward in the increase of computing power. And they have been the platform of choice for simulation and even more recently data processing for many domains, so light sources, LIGO, cosmology, and so on. Maybe not as much in Collider HEP, but also there. And we expect like exaflops of peak performance, so that even a small percentage of that could really provide the processing power we need for high luminosity LHC and others. So DOE would very much like it if high energy physics can take advantage of those resources. Now, of course, that's problematic because of the different compute architecture. For example, most of those compute cycles are being provided by compute accelerators, which we are not using a lot on the grid at all at this point. So what is HEP-CCE, HEP-CCE? HEP-CCE is a 3-year pilot project at 4 US labs for 6 experiments. We have about 12 full-time equivalents of work. And that is about a fractional part of about 30 people. There are 4 sub-projects to HEP-CCE. Number 1 is portable parallelization strategies. So there we discuss and we investigate exploiting massive concurrency and portability requirements. The second one, which will be the main part of this presentation, is fine-grained I/O and related storage issues. So we, as I will show later, we will look into new data models and event batching. Then we have a project on optimizing event generators and one on running complex workflows on high-performance computing. The latter two are somewhat smaller projects, and I will not go into details there, but there are slides actually in the backup, which I stole from somewhere. HEP-CCE is an open collaboration there are meetings which are open, and I copied the Indico page on the bottom. And we also now have a very nice website, which I gave the link for. On the lower part on the right-hand side, you see the project layout. Again, the 4 sub-projects I mentioned on the bottom, they have conveners for each of those. And then we have experiment involvement from all of those experiments, and we have point of contacts there, and we have lab institutional leads. Let me say a little bit about PPS, the maybe biggest sub-project of HEP-CCE. PPS is investigating a range of software portability solutions such as Coco, Sickle, Alpaca, OpenMC. They try doing so by having chosen a rather small number of HEP test beds for each language, such as Paratrack from CMS, Wirecell from Dune, and Fast Carlosim from Atlas. And they define metrics on each of them and try to evaluate support of them. Then they make recommendations to the experiments, which then becomes their experiments job to kind of implement these studies into actual deliverables. For CCE iOS, the goals are to investigate parallel serialization and deserialization of HEP data models. And we are looking at that in both single node and multi-node access pattern. We are investigating persistable data representation tuned for high performance computing storage systems. That we do, will do somewhat in connection with the PPS group and their studies on portable parallelization. And we will also try to take benefit of write once, read many times HEP access models. Then we will study accessing partial and partitioned sub-event data blocks, some of which I will show later. And we will look into runtime memory mapping of data. There we will again work together with PPS to exploit batched or vectorized data and parallel operations on that. Again, here too, taking into account CPU coprocessor communications. As I mentioned earlier, HEP-CCE in general and iOS are open collaborations. iOS meets bi-weekly, Wednesdays from 2 to 3 Chicago time. That's not very friendly to our CERN colleagues, but of course it's the only time we could find, and everyone is invited. Our first year, so we are just 1 year into the project yet now, and our first year activities, we have 2.5 major activities. One is we use a tool called Darshan to monitor root I/O in HEP-CCE workflows on high-performance computing. As you all know, and as we have heard in our first presentation, root I/O is very central to all HEP experiments. And measurements of its performance on high-performance computer with tools such as Darshan, which is a HPC monitoring tool, can give us valuable insights for possible improvements. We are also investigating, even though root is so valuable for our community, we are also investigating alternative storage backends such as HDF5 for intermediate event processing storage on HPC. So there are some workflows, such as for Atlas example, the event service, that create temporary files that can be root or currently are root, but could be something else without a user ever knowing about that. And moving that data into a more parallel file format, such as HDF5, could be beneficial. So we are investigating this. The other really tightly connected activity is we created a testing framework for understanding scalability and performance of HEP output methods. So this is kind of mimicking input and output of our HEP workflows, so that we can then change parameters and analyze the data to see the benefits of potential changes. So let me go into each of these activities and show you a little bit more what we have done. So Darshan for root I/O. So as mentioned, Darshan is a very lightweight I/O characterization tool that can give us a very condensed view of how our application's I/O behaves. Darshan has been deployed at many of the HPC in DOE computing facilities, including the ALFC at Argonne, LCRC, NERSC, and has been a very popular tool with HPC users to understand their I/O workflows. It was originally designed especially for MPI applications. However, then it has been modified to extend to also non-MPI context and can be used for I/O done by root. So what is the status we have? We have integrated Darshan into HEP workflows for 3 experiments, Atlas, CMS, and Dune. And we are able to run that to provide a deeper understanding on how we use our high-performance computing resources. That can help us to optimize the workflow and how we use root. Root is highly configurable in its I/O, and without changing root, the way how we use root can give us fast improvements on the performance and I/O when we do it correctly. So we had 2 phases in the deployment. First was the preparation. We had to get knowledge sharing. We have to do introductions into Darshan, root, and HEP workflows to get the whole community on one level. Then we did do prototype development. We deployed Darshan for the use of those HEP workflows, and there were challenges, such as us using containers, such as us using multi-process strategies that fork processes, and sometimes just the volume of data we did were challenges to Darshan that needed to be addressed and have been addressed to some part. And then Darshan gave us the analysis tools to better understand our I/O behavior. The next slide, I'm showing 2 early plots from Atlas and CMS about these Darshan measurements. And you can see in the upper left, that's an Atlas workflow or multi-process simulation. So you're creating many output files and then they are merged. And you're seeing on the very left hand, you're seeing the worker, and in the diagram, you see how the worker accesses the data from the input file, then processes it to the output file, and then you see on the right hand side how that output is read by the merge process and written into the final hits file. A similar picture for CMS. Here we looked into overlay pileup hits and digitization as one example. And you see the access pattern of that job, how it reads the data, how many read operations there are, I/O operations there are, and the same for writing again. So that's ongoing progress. We have similar for Dune, which I haven't shown here. But that's ongoing progress. We are starting to learn from the Darshan data, and we are starting to feed back to Darshan what needs to be enhanced to fit better to HEP workflows. So we are looking into certain workaround to better instrument I/O workflows, make Dartian more suitable for that. As I said, we had problems with the forking. Complex production environments such as containers are challenging to Dartian. Dartian can get overwhelmed by too many files. It becomes too much data, so we need to give some tools for filtering into there. But that is the good progress on both sides. Dartian is getting better in monitoring HEP workflows, and we are getting better using Dartian. The other activity, the next activity I wanted to show is we are investigating HDF5 as an intermediate event storage backend for high performance computers. So HDF5 is portable and self-describing file format, which is designed to store large amounts of data. And in some way, it's more widely available on HPCs than, let's say, root. And it may be more natural to use there, especially because it should or it does support parallel I/O using MPI. So we are trying to use HDF5 for some of our data, intermediate data. So what have we done so far? Our year one achievements is, so we focus these activities to explore HDF5 for writing HEP data products that have already been serialized with root. So we are still relying on root to do a big amount of work to serialize our complex data model into something which is more blob-like and then gives these binary objects to HDF5 rather than porting the event translation to HDF5. We were to, as in HEP-CCE in general, and also in this project, we are trying to develop experiment-independent solutions. So we have an experiment-independent approach, and we are currently using a multi-threaded testing framework to work with HDF5. So at this point, this is our first attempt to store something in HDF5 style, and it has been done before. We have had a demonstrator for efficient and high-performing data access. There have been a CIDAC program which has stored HEP data in in HDF5 for HPC, but this is now for CMS, Atlas, and Dune, the first approach. And again, we do that in an experiment-neutral way. So we have accomplished in an experiment-neutral way to be able to store root serialized data in HDF5, and I want to show a little glimpse here how this trickles down to the experiments, and I have to apologize that this is Atlas only, but my second hat is Atlas, so I was more familiar with the Atlas example. So once we were able to write root serialized data to HDF5, once we had this experiment agnostic prototype example for that, I remember the ACAD presentation I gave in 2017 about the Atlas shared writing infrastructure. Now Atlas has done run 2 in multi-process mode, and to kind of hide the multi-process structure from our output files, mainly to merge output files on the flight, we have this shared I/O infrastructure since 2017 or even earlier. And we share our output there by using shared memory. Now, to be able to share data via shared memory, you need to serialize the data into shared memory, and for that we use root. Now, that's the very same as we do with our HDF5. We serialize memory and then we stick it into HDF5. So it is a really rather simple change, so that even I could do it, to design a prototype using this new HDF5 knowledge and the older shared IO knowledge, and say, okay, we are now using the root serialization to serialize our data object, but not into shared memory, but stick it into HDF5. And the similar thing we can do on reading, where we say don't read it out of shared memory and deserialize it with root, but read it out of HDF5 and deserialize it using root, and then you have your input data. So this is one example of where HEP-CCE data, where HEP-CCE work being able to store serialized data in HDF5 trickled down to a experiment effort to implement that into the Atlas experiments framework and to have a somewhat hacky prototype of storing data into HDF5. So this is of course not done. We are still working on the tuning. It's not at this point anywhere performant. We have to look into things like chunking and so on. And that's again an effort which will be done as part of HEP-CCE. So this learning about how do we operate HDF5 to be performant, similar to root. HDF5 has many knobs to play with, and we have to learn about that. And many of that is really not particular to one given experiment, but will be useful for all experiments in total. We haven't looked at compression at all yet. And root, of course, we compress our data, and that's a very important aspect of us storing data in root. We haven't considered that in HDF5 yet. Now, at this point, we are only looking into HDF5 for intermediate data, where compression may not matter that much, but still, we will look into that. Using node local storage, we will look into that. And then most importantly, we have to look into parallel IO. That was one of the big motivations for HDF5. We haven't really looked into that yet. More studies about multi-threaded HDF5. Another thing is HDF5 has a direct storage access for GPUs. That's something we want to explore. We have experts for that, and we are starting to look into that as well. So third project, which is in some sense correlated to the second one, is we have created a testing framework for understanding the scalability and the performance of HEP-IO. So this mimics the characteristics of HEP data processing frameworks. It's similar in multi-threaded behavior, similar in IO behavior, and should be reasonably behaving like CMS. People from CMS designed it, but also for Atlas and Doom frameworks. You can easily try different IO implementations, choose what you want, writing to root, writing to plain old data, or writing to HDF5, changing different parameters here. And it's experiment agnostic, as I said, but you can put in actual experiment data products and create root files. So that makes it a lot easier to perform measurements for performance and scalability, which are very important. One achievement here was actually we have used that testing framework to understand serialization, and we found a serialization bottleneck, where you see on the bottom on the left-hand side, you see that the throughput relative to the number of threads, and on the left-hand side kind of plateaus after 4 threads. And that was found to be access to an atomic in root, which was then fixed by root very quickly. And then you see on the left-hand side, much better the scalability and root serialization. Now, those are things which can be found easily by severe stress testing within a mimicking framework. This would be much harder to see in an experiment workflow where things get watered down by reconstruction or simulation or even compression being slow. So we are just entering year 2. What are our year 2 priorities? For portability, they are starting to look into event batching. I mentioned that here because that will be in collaboration with the IO and storage group. The IO and storage group will help with the event batching, and if we have resources, look into data model and storage for CPU and coprocessor communication. We will continue cross-educating each other, the ASCA and HEP activities, and we will continue on the 3 activities I already mentioned. So outlook here. So for HEP-CCE, portability and iOS, I've concentrated on iOS here, have made, I think, significant progress in year 1. We have presented in multiple venues and conferences and trying to get feedback, which so far has been pretty good. We try to foster good interactions with experiments and tool developers. The effort is still ramping up. We started a year ago, it's still ramping up now. Since a year we have COVID, that makes ramping up a little bit harder, but we have been able to recruit developers for HEP-CCE from both HEP and ASCA, and we look into hiring more postdocs and have summer students. So we are very hopeful that we will have a significant impact to the experiments. I hope to have shown some already for Atlas. As I said, that's because my Atlas had, there is similar synergy with CMS and Dune. And HEP-CCE will produce strategies and maybe prototypes, but then of course the production level implementation requires direct experiment involvement. Okay, that's it. Thank you very much.
Okay, thanks, Peter. So let's see, if I look in the live notes at the minute, there's only a question from me, so I don't need to share right now, unless there are potentially other people who want to ask questions. So let me just ask my question. I mean, and I'm cheating a bit because I'm using the fact that we had Jakob's talk earlier on. You mentioned HDF5. Are there any plans to look at RNTuple?
Yeah, so we actually, we have communicated with the root team and also with Jakob in particular, and we are very interested in RNTuple. That said, the main focus of HEP-CCE tends to be more the production framework. And as Jakob has mentioned, we think that RNTuple will enter more from the analysis side and then trickle upstream. But we are interested in understanding RNTuple, understanding what its use in the production framework can be, and even optimize it to a certain degree still. And we had, I think, at least 3 or maybe even 4 presentations from the root team on their storage models.
Unmute. Yeah, so, I mean, okay. Given that you are having problems in introducing this intermediate HDF5 file format, it just seems that maybe RNTuple would be something to seriously consider. It, you know, going through an intermediate data format, unless you're going to reuse that thing. It'd be interesting to understand what the workflow is supposed to be there to make that actually make sense. But Ofer has another question. So Ofer, do you want to go ahead?
Yeah, it was just an addendum to your question, basically, if they're looking at other formats like Parquet and benchmarking between the different formats.
Yeah, so we are not so much looking into performance of different storage formats. We are not doing in performance inventory of different storage formats. That has been done and is interesting work, but that's not what we were trying to do. We were more looking from the functionality aspect. And there are certain limitations which root has had in functionality, like the parallel I/O. You cannot write to the same file from different processes. And we were looking of whether something like HDF5 could help us with that. That was more the aspect there. But then in addition, we will be taking part in the newer root developments, and then especially RNTuple is a very interesting development where we want to participate. Yeah.
Okay, any follow-up, Ofer?
Oh, no, thanks.
All right. So unless I can't see if there are hands up, so let me stop sharing. And David, I think you still have your hand up from before. Or did you have a question?
Oh, sorry, I did, but maybe since you called on me. Peter, this is maybe not, you don't have to answer this if you don't want to, but I wonder what is the motivation for using HPC resources?
Yeah, so the big question is maybe over my pay grade, but I hope that I gave you part of the motivation by showing you that the demand which we expect with HLLHC in computing resources can just not be covered by the traditional grid computing, and at the same time ASCA is planning those high performance computers which have the compute power we need and more. So I think that's the motivation. So then it's just I shouldn't say it's just we of course it needs development in the software framework to be able to use those.
And how, put it another way, what do you think the cost per flop how this would compare with a computing farm?
Yeah, I don't really want to get into that. I think I don't know about the cost per flop when you build Aurora versus a big grid. That I don't know. It may be very well the case that Aurora costs more per flop than a grid would cost. But I guess the point is that Aurora will come no matter what, and Aurora would profit from another showcase client such as HEP, and why should we not take a part of that? Yeah. Did I evade your question well enough?
That's what I mean. I just wanted to see if you had any other answer. Thank you.
Yeah, if you build it, they will come, maybe. So thanks again to Peter. Unless there's one last urgent question, then let's move on to our final talk of the session. So our speaker is Andreas in the Physics Data Services section of CERN IT Storage Group. And well, actually, I'm just going to let you start speaking, Andreas. Do you want to share your slides?
Yes, thanks for having me. Do you see my slides?
Yes, that looks good.
Okay, perfect. So this will be a little bit different take on the whole story because it's more from the other part of the end, not from the application level. So I will make a brief introduction but I was not absolutely sure what the audience is, and many people there are and maybe more expert in some of the topics I talk about than me. So I will skip some parts of that. And then I talk about the medium or short-term perspective of server technology at CERN. And the last part, if we still have time, I want to showcase some of the storage development projects or the direction in storage technology you see where people work on currently. So the preface is that actually for the I/O use case in HEP is still simple compared to what it could be. And when we modify a piece in our storage stack, it can have an impact on all these pieces here. I don't go into detail, but there are many ways you can optimize your I/O stack. If you change a data format, this can have a terrible impact on everything else. So whatever you touch, you must be careful to do the right thing. And it's not always obvious what is the best way to improve something. So there are a lot of technologies or hardware or software approaches you can use to improve I/O. I just flash few concepts you all know probably. So when we talk about disk and tape storage, we have all this client server model in mind because we scale out volume storage independently of the processing capacity. And this is how CERN, for example, mainly does I/O. Most of the I/O is actually that the clients live separate from the server. If you now have this modern, really fast media like flash, you want more this hyper-conversion model because you have like this high performance device actually very close to the CPU. And if you want to gain it, you want to more move in this direction, which is actually not what this worldwide computing at the moment does at the mainstream. Then if you have these two models or you have this distributed computing like we have in storage, you need tiering, you know this. And we have moved to this management model that actually experiments can decide where data lives. While if you have now coming these flash devices, you actually, for this high performance local storage, you can actually envisage to introduce again the kind of access-driven migration to these devices that you don't have to do pre-staging to processors and then schedule jobs there. These are all concepts we discuss in the community a lot, you know. Then we have two access mainstream types. One is just a sequential access with high bandwidth between sites, for example, over wide area network. And when we talk now about these problems of I/O bottlenecks, we mainly look at this local access because most of the access in the frameworks is still happening locally once files have been migrated between sites. And there you find, actually, if you look at CERN, you find a lot of streaming there. There's not so much random access, which is good for us and actually helps us to solve some part of the problem in quite simple ways. Then what Jakob has already mentioned is the way you store your data format. So if you go down to objects, you can group them in a certain way, and you can, normally the storage system doesn't know anything about the structure of your files. So for example, an object storage system can split your object at arbitrary pieces depending what is good for this system. So you don't have full control actually about this. And this is actually an accepted fact. So in the worst part, you can have an object split into many smaller objects because this is what this backend supports. Also, decompression is a big topic which Jakob talked about. The next slide is just about this API. So there's a lot, we have conversion between file, block, and object storage. And this is not a contradiction to what Jakob said, but it's very convenient to have actually, even if you use object storage to call this grouping of objects which you have to call a file and to have an interface to this, because unfortunately we don't have only object storage. So a lot of storage systems use it underneath, but they still expose your files. And if we have to move things around between different flavors, it's still very convenient that there is a top level idea of what is a file, which is just a collection of objects which you then can access actually in the most performant way of an API of an object storage. And the last aspect of this is actually the media. So I'm not a vendor of this I'm not a salesperson of Intel, but they had a nice picture of this, so I used it. And I put on the left side the price, or this is like what you find if you Google it around today and what we pay at CERN. So we actually, what they call the cold tier, we have only hard disk and tape, essentially no SSD, no NVMe or something like this. So this is all in the future of CERN. And the reason is simple. If you look what you get for a given budget is there is only one option. You see already from this graph, if you are limited by cost and you have to make a cost-effective way. And our main problem is still the volume of data. It's clear that we have only disk and tape, and this is only pure media cost, it's not the infrastructure. So if you take the infrastructure, this looks a bit different, but it's still similar. So, but we are, what you also see in this new implementation of I/O servers is that this extreme high performance or latency devices, they are mainly used for doing metadata in the systems. So what is the perspective for I/O, for example, in run 3? So if you write today data formats and applications for the coming period, you will still have a lot of I/O, or most of it coming from disk-based storage systems. And we actually abstract away the tape behind, so no end user actually sees the tape directly, which is good because you can actually write your application with the expectation of having a disk there. So this SSD and NVMe, they're very good for local storage, like burst buffer or caching or temporary files, or this approach that you stage in files and stage them out on a batch node. Therefore, they're really good because they give you high performance. And if you need something like random access, you can easily transform a sequential access from a hard disk into a random access on an SSD by just staging in the file. That's a very simple model, but works effectively. So the main improvement we have here at CERN comes from hardware and software. So we moved to 100 gigabit technology and faster PCI Express HPAs, and we try to introduce parallel I/O from hard disks, so you know all these buzzwords. It's object storage ID or RAIN or erasure coding. These are all similar approach to make I/O parallel and have redundancy at a low cost. And in this model, you can actually provide high performance streams from hard disks. For example, I will show you some R&D we do. We can then assume it's easy to get file access with 1 to 2 gigabytes per second. The question is if the application is actually ready to use it. But on the downside, this is streaming I/O, so you have to be aware in the way you program your application. So this change to 100 gigabit Ethernet gives us 4 to 10 times improvements because we have already hard disks behind this server, which are much faster, but we cannot get out the I/O performance because we had 10 or 25 gigabit interface in the past. Now we go to 100. And we now introduce for some high performance storage that we do client-driven erasure encoding. And this gives you this high performance streams I was talking about. I will have a more concrete example and some results here in the next slide. And as you know, we use X-root server as a modular storage for wide area and local area transfers. So it gives you this access mode for batch jobs and this transfer for remote sites. And now there's also this possibility to use it for caching, which we didn't exploit at CERN. But the model is very simple. There's a remote client, an X-root server, which in some way delivers I/O from a hard disk. So on the large scale, this looks like this. This is a few days ago. We have now around 100 gigabyte per second reading at CERN, 10 to 20 gigabyte writing. Only 436,000 I/O ops, which means this is good because it's hard disk, and which actually means we have like 10 to 20 I/O ops per disk, which is not really a problem. But this in the future, we will have to deliver more I/O. And the question is now, what do we do to do this? So the general direction, as I mentioned, is already that we in the future give more bandwidth to the data and at lower cost possibly, but you will also lose some of the I/O operations capacity, and this will have a result for experiment users that they have to deal with possibly much larger files. So I don't talk about the metadata part, but in all this is assumed that an experiment can grow its files linear to what the requirements of the bandwidth are. So this year we will get like close to half a exabyte at CERN, and a typical storage server at CERN looks then that you have 14 terabyte disks with 96 disks per server, and they have a 100 gigabit interface, and there's no blocking factor on the network. There's also a high performance setup coming for the ALICE experiment, which is called O2. This is a dedicated 100 petabyte pool, which has 75 of these big machines. And we want to run this with erasure coding, or they want to run it with erasure coding with the 10 data stripes and 2 parities for cost reasons. And what we expect now from measurements is that we think we can run this at 2 terabit streaming I/O with client-driven erasure coding. In all this model, we don't use really SSDs or NVMEs on these storage nodes. There will be NVMEs for analysis facilities with hyperconverged CEFFS as an example. So the hard disks are still much cheaper than SSDs. Also, they use more electricity, but at CERN, this is not really a big concern in the near future. Tape are still cheaper, so we have a quite equivalent setup of tape at CERN. But there is in principle the alternative approach possible that at some point you replace part of this or all with erasure coding on this if this gets cost effective, or actually the I/O requires it, because this system with erasure coding has much nicer access pattern than the tape system, which is more complicated to get actually the data to be accessed now. So if you look in our statistics, most of the I/O we see is actually still essentially sequentially. So you have people uploading and downloading complete files, or you have this typical root I/O pattern that there are few initial seeks and then you go forward seeking in the file, either take the whole file or you just look for parts of it. But still, this is quite friendly for on hard disk. So what I was saying about this O2 use case is we are testing a prototype of client-side erasure coding, because one of the problems with erasure coding is that normally you have more clients and servers. So to do all the encoding on server side has a price, but in particular, the price you have to pay is actually tails in up and download transfers. So if you do server-side erasure encoding, you have a coupling between the machines, between the disk, and the I/O flows normally through one machine to the neighboring nodes. While in this client-side, client-driven erasure encoding, the client writes the data and the parity directly, and if you read, you only have to access the data stripes. So the network load is essentially half if you have large data stripe sizes. And what we see in this test is that we can, in this system for ALICE, for example, we can have streams of an average of 1.8 gigabyte per second with this 10 data plus 2 parity stripes. And if you look at this tails of the distribution, there's like a time budget for the DEQ system, which will inject data into this pool. So we will be able in this test, actually, we can, with the time budget we have, we can be always sure that no data is stuck in this DEQ system, which will be 800 GPUs, which sort of do a sort of event building process there. So, you know, I mentioned already why we use XOD. There are many reasons. Now, if we go to 100 gigabit networking, it's important actually, how is this a good framework for 100 gigabit networking? And in the future, we will also introduce SSDs and NVMe flash. Is this still a good client-server framework? So there are a few numbers here I show you. This is just, you know, XOD can run also as an HTTP server very easily today. And actually the best method to get single stream performance on 100 gigabit Ethernet is just something like a curl. So you download a file, we do this with Davix here, and you get actually with the single stream 3.5 gigabyte if the data comes from memory. If you use root protocol, it's not a single request where the server pushes the data. There are many requests, it's a bit slower, but they are actually working to improve this. So this is what you can get from a single stream on 100 gigabit Ethernet if your client and server have that. So now we serve to many clients, so we want to see, can we actually exploit 100 gigabit with this hardware? And in a test already with 10 streams, you can actually saturate, if you serve data from memory, the 100 gigabit Ethernet. And if you look at I/O provisions of XOT, you can measure that if the data comes from the buffer cache, you have close to 2 million I/O ops. So there is no real problem in such a server. But now if you put an NVMe device and nothing is in the buffer cache, the way xroot async I/O works, it's one of the oldest possible implementation. It's not very good for this device. Still, it gives you 40,000 I/O operations. And if your operations are big enough, you can still saturate this pipe from an NVMe. So here are some other tests, because in the end, we don't have memory, but we have in our deployment, we have 96 disks. And what we get, if you include also the I/O on the controllers and the backplanes there, we actually managed to read and write 10 gigabytes per second from one client to one machine, which is nice. So now this means you have to build applications which actually require this on client side. So there is some CPU for sure used the way the xroot client is implemented. So we made also some other experiments where we have actually a gateway to some other storage behind at CERN. We have, for example, Ceph, and the bottleneck actually there is not in this xroot remote access. It comes actually from the kernel client of Ceph itself, where we managed to write 6 gigabytes per second, and we can read 3 gigabytes per second. This can be probably tuned, but this is what we get out of the box of such a system. Since some of you work in HPC systems, another storage server which is used for data transfer is this Globus Connect version 5. Due to this commercial idea now behind Globus, WSG is actually popping out of this Globus as a platform. And actually, we don't have support currently in this file transfer server to use it, but since this is a kind of standard in high HPC deployments, it's probably necessary to sort of get this connected to the rest of WLCG. So I don't know if I have still some time. Yes. The last part is a bit about to see what others do. So this was what we do at CERN. A lot of the things are actually just driven by the cost model. Okay, but other people they develop in other environments like in HPC computers. So if you look which other I/O systems are out there, there are many. Maybe you have not even seen them, but some of them are really worth to look at because they are nice add-ons on top of existing systems. For example, on object storage to get a very performant file system access to object storage like this Juice FS, which is rather new. Or there are parallel file systems for HPC, which you probably know very well. Then there are other storage systems which we don't use at all, which are distributed key value stores like ScyllaDB. And there are others which we know well, but for price reason like Amazon S3 or Google storage, which are not here in the mainstream of our environment. So some of these trends are, all these people working in HPC, they try to get rid of POSIX, but in the end, they still provide you then a fuse file system to read on top of the object storage, which is sort of funny, but it's probably because application use still this POSIX I/O model. And you see a lot of parallel I/O with object storage. There are also it's not only us doing this client-side erasure encoding. I have this other project, which is this NVMesh, which also does object store with client-side erasure coding, extremely low access latencies. And these projects, they also use NVMe and persistent memory like this Intel Deos and things like this. So the problem, if you have this is now a little bit about these new storage media, which are coming, but still a bit expensive. If you use NVMEs or obtain memory, you can quickly understand if you use the asynchronous interface in Linux, that is not very efficient. At least the one we have deployed at CERN with the kernel version 3, or if you are lucky, you have kernel version 4. So if you have a device with microseconds, they don't work very well. An example is, for example, you deploy Ceph and you put very nice NVMe devices inside. And then you hope that this high performance node would deliver all these IOPS of these NVMe devices. It's currently not possible because the implementation, how you do IO or asynchronous IO is very inefficient. And even if you have a very high performance format, as an example, you get 80,000 IO ops with 6 milliseconds latency from a server to a client, which is for what you want to do is not the idea. No? And where does this come from? So there are new frameworks like, for example, this ScyllaDB. They use something which is called C-star framework, and they go from this interrupt-driven I/O to a polling I/O. And you can see in this picture here that this saves you some time. So what you do is you trade some CPU time for lower latency. And on the right side, this is a plot from Western Digital. You can see actually for some devices, you absolutely have to go this way because you can actually then profit from this low latency device in this way by actually using polling I/O. Something which Jakob talked about is this IO-Uring. Just a brief explanation about in Linux, you have like the normal synchronous interface everybody uses and knows, read and write. Then the simplest incarnation of asynchronous I/O is called POSIX I/O. This is just a set thread pool executing this read or write calls. Then the next one is Linux AIO, which only works with direct I/O, so you don't have buffer cache involved in this. And it's, according to Linus Torvald, it's a terrible thing. And that now in, I think, 2019, they came up with a new kernel to have this U-ring, which is a real asynchronous interface. And actually, if you, for example, want to use something like XOD on this NVMe devices, you would have to go to such an interface to profit from what these devices can give. So this internally is just a submission queue where you actually, application can asynchronously put a request, and then there's a completion queue where the kernel then, once the request is executed, put the result to be taken out by the application. So it's a very simple way, but very efficient. So last thing I have are actually a few examples of these very modern alternative ways of I/O. So one is a commercial product, which is called NVMesh2. So they have a patent method to do remote access to NVMe, which bypasses the CPU. So they sort of go from the network device directly to the NVMe device. And the results or the thing you can buy is really impressive. Let's have a look here. So it's like a remote flash storage, which you can attach where you want. They have a nice configurator here where you can play what such a system can do. You get extremely low latency access, and they actually provide also this erasure coding on client side on top of NVMe. So you can read, for example, 770 gigabyte per second from flash with a write latency of 100 microseconds. The downside is actually then the size of such a system, but it's in the end, the idea is to provide on the fly, very fast remote NVMe devices, for example, to VMs or something like that. But it's an interesting, very interesting storage platform. The second one we have seen, this is this distributed asynchronous object store of Intel. Software is free, but you pay them for the nice hardware. And they say they replace everything which is a hard disk on the left side in the conventional storage system. For metadata, they use this extreme low latency persistent memory or RAM or NVMe. And then you have SSDs or NVMe for the data part. And for sure, this system has also extreme low latency. You don't have the problem of context switches also on the client side. It's really, you can really do very fast access. That this works, you can see they managed to enter this IO 500 list on the top, but they have already been beaten by somebody else now. But if you look also in the roadmap of this project, there's still quite some work to do and things to come. So it's not a done deal, this DAO, as you already mentioned. In Ceph, there's a similar activity going on. So they rewrite this OSD, which I said has this problem of delivering IOPS of these high IOPS devices. And this is called, the codename is Crimson. It's quite long, so it's already a year they work on this, and it's not finished. And they also replace what they just developed to combine NVMe and hard disk, which is called BlueStore, with another store, which now uses this new kernel interface to actually be able to deliver from an OSD this high I/O. So this very interesting project, not done, but there's also still some work to be done here. This is something which comes from US. I don't know too much about it. I've seen one from the university. So the idea here is that you actually process data inside the object store. So in this case, it's a Ceph object store. This is called Skyhook DM, and it gives you row-based processing with flat buffers and column-based processing with the Apache Arrow. And there was such a case, you can look at the link down where they evaluated how is it better than doing this remote I/O or not. And for sure, depending how much you select, the less you select, the better it is actually to run locally on the data. What is the approach of such a system? So you benefit a lot from this locality here. But for example, if you have an erasure-coded object store, the benefit is not so obvious because you have most of the pieces in a erasure-coded object store come from remote, so you can also actually fetch the pieces to a client, and there shouldn't be such a big difference in doing that. While it's clear if you select a lot from the data, it's a very nice R&D. Actually, you should get very good results. The question is this something to run an LHC framework? Probably not. And is actually the benefit you get of it worth to make such a dedicated storage system? This one has to see comes out of the future. So I come to the summary, which is sort of some of the things I just said. So these I/O requirements, I think they are much less problematic than the CPU, which has been mentioned also in the previous talk. So by just doing this step forward to 100 gigabit Ethernet and give our clients this feature of parallel I/O, we can go to very high stream, and then it will be up to the application actually to be able to put this on a 64-core machine and be able to process this data which we can inject. So the SSD and NVM is very useful for this ad hoc storage. At least this is a CERN approach. So you have every batch node, you could have this NVMe or SSD. But if you want now to put up a storage system where, like for analysis use cases where you need a lot of random access, we would have to work, since we at the moment use mainly XOT, we would have to work, or the XOT people would have to work actually to use this more modern asynchronous I/O of the Linux kernel. And the other question is actually, if you look how slow we are in deploying new kernels, you need kernel 5.1. When will this be at CERN? I cannot tell you. But the workaround to use high performance is actually to do it locally, like the root people have integrated already this IU-ring. Or you just don't do too small I/Os, and you mainly benefit from the bandwidth of these devices. So now if you look a bit over the edge of what we do, you see that open source storage software is quite mainstream. All these big players, they provide it sort of for free, because that is a way to get actually also your hardware sold, no? To use them efficiently. And while this is very exciting, I think in the current situation like CERN is, this is, you observe that and you can try to make R&D with it and provide some small dedicated system for such a thing, but it's not really, will not have any big impact soon on the mainstream, how I/O happens at CERN and which volume is transferred to the applications at CERN. That's it. I thank you very much. Just the last thing, if you're interested in what we do at CERN here, we have a workshop about EOS storage system. The beginning of March is a virtual workshop, no fee. You can just have a look. There's also quite something about XOT and this framework. Thank you very much.
Thanks very much, Andreas. So I see again, actually, that I'm the only person who's written questions in the Google Doc in the live notes. So let me first go to the room. Maybe there are some questions in the room. Okay, Doug, go ahead.
Yeah, on your summary slide, you talked about the open source storage software. While right now it doesn't sort of fit in with what CERN's doing, sort of run 5 timescale. Do you see it sort of we becoming more mainline with that kind of activity? Because that's obviously a bigger audience.
What do you mean by open source? Open source is software which is open source.
But
So
I mean,
all the software I talked about is open source.
Software you said has become mainstream, but it's really not something. Your last box.
Yes. No, I mean, what I wanted to say is that if you look these big projects which are proposed like DEOS or all this, besides this one which I mentioned was this NV Mesh, which is a pure commercial project. A lot of radars have everything. These are open source big projects, and also the CERN software, XOT is open source, EOS is open source. And also these big vendors, they go this open source idea, and we can actually profit by a lot of these frameworks like you saw that in the end, they all now have to do the same. They have to improve the asynchronous IO interfaces. And at the moment, since we are very much cost driven, what we do at the moment is the most sensible thing for the CERN perspective.
Okay, so let me take the liberty of asking my, this is a very chairperson sort of question, Andreas, but we're thinking about the future of IO and storage. So how do you think the future of storage really looks? I mean, I was particularly interested to see there's just a factor of 2 between disk and tape, and particularly thinking about, if you think about the risk factors for the number of tape producers, and assuming that tapes continue to go in the direction that they're going in, do you think there could be a point where there would be a stronger push to move away from tape and move towards disk? Or so how do you see the future landscape looking in a few years?
I personally think that there will be the point where we can easily give up on the tape technology. It's not now, but it's not so far away. So there are not order of magnitude differences. If you consider all the facts which play a role in this, it's not sometimes because a tape is cheap, but the infrastructure and the software in the end has to come from somewhere. And the availability of data, if now this IOs goes faster and faster, the question is if it's still a model to stage data from tape in this manual fashion, or at some point actually it's just fine to leave the data on disk, because our disks, I think the average lifetime is a 5 years period, and we regularly drain these machines. So it's not very different from rewriting tapes in the end. And it's not that we lose 10% of the data just because we have disk. So we have quite some experience on the stability of the data. No? For sure, the worst incident on a tape is much better than the worst incident on the disk system. So if you look at some of these products, it's easy to do a mistake and delete everything within minutes. So that's the danger here. And one has to put a lot of protection that this is not possible. But I see actually this coming at some point.
I'd like to follow up on this only in the sense that I assume you're separating archival storage. By that, I mean stuff that you have a fiduciary responsibility to keep, like raw data from a collider.
Yes.
Versus data products that can be reproduced and reused. Because obviously while there are fewer tape vendors and there is some risk, we're not the biggest tape consumers in the world.
Sure, yes.
But my point is that I think there's always a need for tape. You'll never go to a purely disk system.
Discuss. Andreas, your response.
Yeah, I mean, this is mainly to convince yourself that it is safe enough. I mean, the value of the data is extremely high if you consider the cost of producing raw data. So to lose 1 per mil of it is not a problem, but if you have like an incident that you lose 20% of past LHD ones, this would be a real disaster. So I think the threshold to move away from tape, it's still there. But it could be at some point, could be the time that the other argument of the price and the landscape of the technology is much stronger than this threshold to actually dare to do that. There are already initiatives, like I said, this KISTI project where they replace, because for smaller sites, actually, a tape system is not so cheap to have. No, you need dedicated people who know how to use it, or you have to buy the service. And on a small scale, a tape system is not cheap. On a big scale, yes.
Okay, thanks a lot. So are there any other comments or questions? Okay, I don't see any hands going up. So I think at that point, then let's thank all of our speakers again. Thanks a lot for tuning in today, and we'll meet again. Remind me of the date, Marcus.
It is March 2nd.
2nd, that's the one. Very good.
And we will talk about best practices for starting a sustainable software project, or making an existing software project sustainable.
Great. So hopefully we'll see you all again in just a few weeks' time. And thanks again to all of our speakers and for joining us today. Thanks a lot. Bye-bye.
Thank you. Thank you, Paul.